I came to NASA Langley in 1960, fresh out of college, 22-year-old. And my first assignment was to work on meteoroid protection for spacecraft. We didn't know much about meteoroid protection back then. We knew that we knew about meteors. Scientists had studied the flashes of light caused by meteoroids when they enter the atmosphere, the meteors. But we didn't know how many there were, how big there were, and how much damage they would do to spacecraft, and what it would take to protect our spacecraft against the impacts of meteoroids. So I began studying there. Already when I arrived, we had a facility with light gas guns in it to simulate meteoroid impacts. The light gas guns that we had down there are guns that are much faster than a rifle, maybe 10 times the speed of a rifle. And so they better simulated the meteoroid impacts, which are very high. But they were only simulating the lower end of the spectrum of velocities from the meteoroids. The average impact speed of a meteoroid striking a spacecraft that's orbiting the Earth would be 20 to 25 kilometers per second. The guns that we had could shoot up to 10 kilometers per second. As time went on, there was another hazard that developed. The more and more we used space and the more satellites we put up, we started leaving debris in orbit around the Earth. And that turned out to be a pretty big problem. The debris would start colliding into other pieces of debris and creating even more smaller pieces of debris, but many more of them. And so by the time we got to putting the International Space Station into orbit, the threat of damage from man-made debris was greater than that of the meteoroids. We wanted to study the whole spectrum of impact speeds that we were capable of attaining in the laboratory on targets, what damage they would do, and on simulated spacecraft walls. So we used rifles to do the lower impact speeds. A conventional high-speed rifle, commercial rifle, will shoot about 1 kilometer per second. You can take a rifle like that and modify it and double the speed up to 2 kilometers per second by taking the lead or copper bullet out, steel bullet, out of the cartridge and putting in a plastic bullet. Plastic lighter will go faster. And you can use pistol powder in the rifle instead of rifle powder. That burns faster. Another thing is the bore of the gun. Conventional guns have rifling in it that stabilizes the bullet on its flight. That's not needed in the laboratory because the targets that we shoot are only placed a few feet away from the gun anyway, and it's in a vacuum tank. There's no air there to throw the projectile off track or to slow it down. So we could do impacts up to, say, 2 kilometers per second. But there's a limitation on regular rifles caused by the fact that the gases that propel the projectile are nitrocellulose gases from the burning gunpowder, and nitrocellulose gases are very heavy, and there is a limit to how fast a nitrocellulose gas can expand. The light gas guns we had were very large, and they had 22 caliber launch tubes, the second stage, and like 20 millimeter pump tubes, which were the first stage of the gun. And the barrels were very long, 5 feet long or so, and very expensive, very expensive. And in trying to obtain the highest velocities, you always wanted to get the highest velocities because we were at the low end of the actual impact speeds that meteoroids would produce. You want to push the gun, but when you push the gun, you tend to wear it out. And these are very expensive parts, and so you wanted to be careful. What I decided to do was to see if I could build a miniature light gas gun and keep the cost down and still obtain the same velocity. I didn't know whether I could obtain the same speed or not, when in fact, as it worked out, we were able to get just as high a speed. And here at Langley, we got the highest speeds we obtained were on that one because we were not afraid to push the limits of the gun and have to replace parts, because The part needed to replace most often is the launch tube, the second stage where the projectile is in. And what I did was to buy some superpressure tubing and use that as the second stage. Superpressure tubing it can, as the name says, withstand very high pressures. But there are also very close tolerances on the inside and outside diameter of the tube, so it's good for a gun barrel. The small light gas gun that I built only used a 1 foot long launch tube, and that piece of tubing only cost about $1. So it was no high risk at trying to push that gun to shoot as fast as it would shoot. The first stage of the miniature light gas gun I used was just a conventional rifle, a .220 Swift, which is the fastest gun that you could buy, and is as fast right now as you could buy, at about 1 kilometer per second. And as it turns out, it was very successful. We have achieved impact projectile velocities over 9 kilometers per second. And these have been used for a number of studies to answer problems that we had and questions we had about impacts that are going to occur in space. First thing I will do, this is an empty cartridge. It has no primer in it, no gunpowder in it, no bullet. I will put a primer in here, put the shell in there, and press the primer into the bottom. I'll put a small O-ring over the cartridge. It's going to provide a seal when the gun is loaded with hydrogen. We use pistol powder instead of rifle powder because it burns faster. The gunpowder, the amount we use will not fill this cartridge up. Maybe it'll be halfway or so. And to keep the gunpowder from slumping when we tip it horizontal, take some cotton and put cotton, a little wad of cotton in there, and press that cotton down. With that ready, take one of these high-density polyethylene pistons, insert it into the end of the cartridge, and it's ready. This is the gun barrel that the projectile will be put in. It's a piece of high-pressure superpressure tubing. This will go into the guide tube. The end cap placed on the end. Is screwed in until the gun barrel, the launch tube, just protrudes ever so slightly. This is the compression block that goes between the pump tube and the launch tube. It's tapered in size from the .220 on this end to about 1/16 of an inch on this end. The diaphragm that will hold back the pressure is put in this end, and an O-ring on top. An O-ring also goes in the other end. The piston will come down into this section, and being high-density polyethylene, it's easily deformable and not very compressible, so it will easily take to the tapered shape in here and become lodged in this compression block. I'm setting up a light gas gun for a test. This is the pump. This is the launch tube that I'm inserting into the test chamber. And this is the compression block that will be between the launch tube and the pump tube. With these all snugged, come back here and put the cartridge in this end. Put it into the gun. This is a .220 Swift rifle. The next thing to do is to start the vacuum pump, which will evacuate the test chamber and evacuate the gun barrel up to where the projectile is located. After that, we will open the valve to the pump tube. Now, the vacuum is not pumping between the diaphragm that's in here and the bullet. But we're going to pull the air out with a separate vacuum tank. And when it is evacuated, we'll close off that vacuum pump and bring in hydrogen, pressurized hydrogen, from a bottle outside the building into this tube. And once it is pressurized, we will close that valve, closing up the pump tube. Now we're ready to shoot the gun. I'm taking out the safety, prevents it from going off prematurely. The gun's going to be fired by pulling this cable from behind a shield there. When the trigger is pulled, the gunpowder in the cartridge will ignite and push that piston inserted into the end of it down this tube filled with hydrogen. It will, as it goes down farther and farther, the hydrogen gets compressed to greater and greater pressures. It will come all the way down to somewhere around here when the pressure exceeds that which this diaphragm can withstand. The diaphragm will burst, and this hydrogen gas will rush on through, hit the projectile, and push it at high velocities through the launch tube. Hydrogen gas is as light a gas as you can have, and it will expand much faster, and therefore it's capable of pushing projectiles to a much higher speed. When the projectile comes out of the gun barrel, it will pass through a beam produced by this laser. The laser beam comes through that window, out a window on the bottom, hits a mirror, comes over to another mirror, comes back up through this window into the detector. That detector is hooked to an oscilloscope, and we'll get 2 blips on the oscilloscope, one for each time that it goes through the laser beam. And knowing the distance between the 2 windows and the time it took, we'll have the velocity of the projectile. Projectile will travel on down to wherever the target is placed. Typically, the target would be placed inside this chamber. In some cases where we have very large targets that we want to test, targets will be put in this large chamber. One way of varying the speed at which the projectile will come out of this gun is by varying the thickness of the mylar diaphragm that is put in the compression section. The second way is to vary the amount of gunpowder that is put into the cartridge, and the third way is by varying the pressure of the hydrogen that is put into the pump tube. To fire the gun, I'll come back here, and I'm going to put on these air muffs in case the seals fail, and it will make some noise. If this fires properly and the seals hold, there should be no noise except the clicking of the gun. That's the shot. As time went by, I got into more aspects of the meteoroid problem, such as sending experiments into space to actually measure how many impacts occur and how damaging they are. The earliest one of the earliest ones being the Pioneer spacecraft that were sent to Jupiter. Those 2 spacecraft, Pioneer 10, Pioneer 11, went through the asteroid belt, the first 2 spacecraft to go through the asteroid belt. This is the asteroid belt, which is a belt between Jupiter and Mars, in which there are thousands of rocks that we can see with telescopes from the Earth, going in nearly circular orbits in the ecliptic plane around the sun. And we were going to travel through the ecliptic plane and through that belt, and we wondered how much damage there would be. We were kind of a test to see. And so I was part of the one team that had an experiment on there to measure meteoroid impacts and the impacts of the asteroid belt particles on a spacecraft. And what we found out was that it was really no big problem for small spacecraft. Pioneer 10 went through the asteroid belt. As it approached the asteroid belt, it was recording impacts at a certain rate. When it went into the asteroid belt, it continued to count impacts at that same rate. And when it came out of the asteroid belt, it still continued to count at that rate. So there was really no detectable asteroid belt to spacecraft, the size particles that hit on it. The probability of it running into one of the really large ones was extremely small, and as a matter of fact, it was calculated, and they knew ahead of time we were not going to collide with any of the big things in the asteroid belt. while the Pioneer 10 and the Pioneer 11 spacecraft never came back to Earth, they escaped the solar system. They're still out there going somewhere. We put up a satellite called LDEF, Long Duration Exposure Facility, in Earth orbit with the intention of bringing it back. And there was very little instrumentation. In fact, there was, I understand, no communication between the satellite and the ground, no telemeter data back. So all data was gathered by bringing the spacecraft back. And I was lucky to be an experimenter on that. And what I did was to expose a large number of aluminum plates to the space environment with the intention of then counting all of the craters that were there, measuring their size, get the size distribution, and try to do some analysis of the material lining the craters to see if I could find any of the projectile material that caused that crater, and determine primarily whether it was a meteoroid that hit it or was it man-made debris that hit it. We wanted a comparison, want to know how those, both of those threats, the magnitude of both of them. And cataloged more than 10,000 craters that I found on there, small ones being, you know, on the order of 10 microns or so, very small ones. On up to the largest crater, which was about 1/4 of an inch in diameter. One thing that strikes you right away is how similar they look to the craters that we could produce in the laboratory. Almost all of the craters are hemispherical, or very close to hemispherical, so that the shape of the impact speeds are so high that the shape of the projectile doesn't show up in the final outcome of the crater. The astronauts who took LDEF up and brought it back, those astronauts came into my lab and they wanted to see what I had found, and so I was able to show them what we got out of it, and that was very rewarding. When I was still working, I worked on the LDEF data for many years. There was so much data there. So many things we found. I wanted to examine more and more craters to see if I could find part of the impactors in there. Again, to see how many were meteoroids and how many were man-made debris. And so I was continuing to work on that when the call came for me to help work on the shuttle tiles. The vacuum chamber I had at the light gas gun was used then as a chamber to test some repairs. I built a device that would allow us to put a shuttle inside the tank, evacuate it, and then have arms come over and to the surface and to apply fillers to the damaged tile and to smooth it out, and to see whether under vacuum conditions the kind of fillers and that, whether you could actually do that in space. So I worked on that for some time. I'm retired now, and I worked here for 44 years, and it was a wonderful time the whole time. And the things that I did kept changing with time. It was still meteoroid studies for years and years and years. The first 30 years, the only craters I had ever seen were simulated craters that I had produced in the laboratory. And finally, after about 30 years, actually spacecraft parts were being brought back, and I was able to see what real craters look like. And I could compare then what I had been doing, trying to simulate impacts with what the real impacts look like. And that was a great joy, and I enjoyed every minute of examining those craters. I loved everything I did. It was great. Of meteoroids. So I began studying there. Already when I arrived, we had a facility with light gas guns in it to simulate meteoroid impacts. The light gas guns that we had down there are guns that are much faster than a rifle, maybe 10 times the speed of a rifle. And so they better simulated the meteoroid impacts, which are very high. I came to NASA Langley in 1960, fresh out of college, 22-year-old. And my first assignment was to work on meteoroid protection for spacecraft. We didn't know much about meteoroid protection back then. We knew that we knew about meteors. Scientists had studied the flashes of light caused by meteoroids when they enter the atmosphere, the meteors. But we didn't know how many there were, how big there were, and how much damage they would do to spacecraft, and what it would take to protect our spacecraft against the impact. The more and more satellites we put up, we started leaving debris in orbit around the Earth. And that turned out to be a pretty big problem. The debris would start colliding into other pieces of debris and creating even more smaller pieces of debris, but many more of them. And so by the time we got to putting the International Space Station into orbit, the threat of damage from man-made debris was greater than that but they were only simulating the lower end of the spectrum of velocities from the meteoroids. The average impact speed of a meteoroid striking a spacecraft that's orbiting the Earth would be 20 to 25 kilometers per second. The guns that we had could shoot up to 10 kilometers per second. As time went on, there was another hazard that developed. The more and more we used space and